If the sun were to vanish instantly, we would not notice it right away. This is because light, traveling at the cosmic speed limit, takes about 8 minutes and 20 seconds to cover the 93 million miles between the sun and our planet. During this interval, the Earth continues to receive the light and heat emitted before the disappearance. Our perception of the sun remains unchanged, locked in this silent grace period. Gravity also travels at the speed of light. For those first 8 minutes and 20 seconds, Earth would continue to orbit the empty space where the sun once was, following the same gravitational path. We remain tethered to a phantom star until the gravitational influence vanishes. 8 minutes and 20 seconds have passed. The light from the sun finally stops reaching our planet. In an instant, the transition from day to night becomes absolute. Daylight vanishes as the stream of photons is severed. The moon, which relies entirely on reflected sunlight, disappears from the sky simultaneously. The Earth is plunged into total, unexpected darkness. Once the light stops reaching us, Earth wouldn't plunge into instant, absolute darkness. For a few seconds, our atmosphere continues to scatter photons, creating a faint, eerie twilight glow. This light rapidly fades as the atmosphere runs out of residual light to scatter, leaving the planet in cold cosmic darkness. Would we freeze? Not for just 1 minute. Earth's atmosphere and oceans have immense thermal inertia, acting as a colossal battery that stores heat effectively. Temperature is a slow-moving metric. Even over centuries, as seen in global climate data, shifts take immense time to register. A 60-second solar blackout would result in virtually zero change to surface temperatures, keeping the planet as warm as before. Once the sun's gravitational pull ceases, Earth no longer stays in a curve. Instead, it follows the law of inertia, traveling in a straight line tangent to its former path at 30 kilometers per second. This diagram shows how gravity normally pulls Earth toward the center, maintaining a circular path. Without that pull, only the tangential inertia remains. In just 1 minute, Earth would drift approximately 1,800 kilometers off course. While this distance seems vast, it is a very minor deviation in the scale of an entire planetary orbit. Our modern global infrastructure relies on the ionosphere, a charged layer of our atmosphere. This layer is maintained by constant solar radiation. A sudden drop in solar radiation alters ion density. This triggers chaotic disruptions in high-frequency radio waves and global GPS timing systems. Even if the physical planet remains stable, satellite synchronization would fail, affecting everything from financial markets to precise navigation technology. For 1 minute, technology would experience a silent, global blackout of navigation and communication. The greatest danger of a solar blackout isn't physical, it's psychological. The sudden, unexplained disappearance of the sun would trigger unprecedented global panic. Human response is the real catastrophe. In a moment of total darkness, the lack of explanation would drive immediate worldwide instability. The human brain reacts to such extreme, acute stress by activating survival circuits. Logic is suppressed by panic, and the sudden environmental threat triggers an immediate fight-or-flight response across the entire planet. While the Earth remains physically intact, the sudden loss of our cosmic anchor would challenge the resilience of human society. The true catastrophe of this minute-long event is not in space, but in our reaction to the dark.